do some more schemes which are better schemes than Euler. Then I will show some demos. Okay. So I will hope to finish ODEs today, and then we'll start PDEs. So just to recap, we wanted to solve x dot is fxt numerically. So I showed two algorithms, Euler forward and Euler backward. I am going to change my notation a bit for future. So this was x, I wrote subscript n plus 1. So I will write like this, n plus 1 equal to xn plus h f xnt. So that is forward Euler, and x n plus 1 equal to xn. So this is time something like nth step. Okay, this is the number, which step are you in, that is what is telling you, plus h f. Now here I have to compute at n plus 1. Okay, so this is a better notation, it will become clear towards the end of the class. So there are two important concerns. One is accuracy. So it should be accurate method, not inaccurate, so then your answer may be very much off. And second is stability. So this stability is somewhat different than your usual notion. It is defined for, so if my solution is going to a constant value or going to a some value, asymptotic value, my numerical solution should also go to the asymptotic value. Well, not that value, should not deviate, it won't go to that value. In fact, it's quite clear that if your method is not accurate, your solution from numerical scheme could be very different than the asymptotic value, but it should not blow up. Okay, so that's the condition. I hope it is clear to everyone, and we need to be certain that these two conditions are satisfied by the algorithm. Well, I mean, sometimes you may still use schemes which are unstable, but you have to be careful. Sometimes it is very difficult to prove stability for all parameters. Okay. So now today I want to discuss one more scheme which is stable, but which is better than Euler. Okay. So that scheme is trapezoid rule, based on trapezoid rule. So I can solve this one as xn plus 1 is xn plus, so trapezoid rule is combination of the two. So in fact I just combine the two, f xn tn plus f xn plus 1. So I put a factor half. Okay. So this system is more, well, is will be more accurate because I am taking two of them, xn and xn plus 1. Also it happens to be more stable. So how do I prove stability for the problem I was doing in the last class? Suppose my equation is x dot equal to alpha x, then how does it translate? So xn plus 1 is xn. Now this is fx, please remember this is fx. Okay. So h by 2 now is going to be alpha xn plus alpha xn plus 1. Right, I am substituting. So this implies that xn plus 1 is xn So I will have this plus this. So 1 plus h by 2 alpha and 1 minus h by 2. Now for alpha negative, the problem, remember, it was for alpha negative. For alpha negative, what is this? This quantity is always less than 1, correct? Alpha negative. So the system is stable. What about alpha is I pi, purely complex? If it is purely complex, then again mod is 1. Okay? For purely complex, so it is unstable. It is at the borderline, but is better than being unstable. So this is another implicit scheme. It is this scheme we use it quite often. This is called Crank-Nicolson scheme. Okay. So I will show you. In fact, we will need this for future. So some scheme you have to remember, like Crank-Nicolson will be a important scheme. This scheme we will use it in when you solve PDEs. Okay. Now let us do slightly better schemes. So 1, 2, 3. So this is the third scheme I have told you. Okay. So we will have lots of them. I will not cover lots of them, but I will just show you something like 4 or 5. So another class of schemes called predictor-corrector. Schemes. So predictor-corrector schemes. So let's do one. How does it work? Predictor-corrector. So look, I don't know this guy, no. That is one of the key problems. Here I don't know this, so how do I compute it for arbitrary fx? This was easy, but for arbitrary fx will be a problem. So what we do is I first predict, not that won't be the exact value, but I predict. So I predict xn plus 1, I call it star. So it is a predicted value by Euler scheme. So just use Euler scheme to predict. So it is going to be xn. So h f xn t. So I made a prediction. What is the x star? Yeah. So a question.
So the second equation, Euler backward.
Okay.
So do we know fx n plus 1 t n plus 1?
You don't know, because, so please remember, so we are going from time Tn to Tn plus 1. Okay. So I know the value xn and Tn, and given function f is a derivative, numerical derivative. Based on f, I want to go to the future. This one, yes.
Should it not be xn instead of n plus 1?
No, that is called implicit scheme. So I am writing my solution in terms of xn plus 1. Okay. So it's true that I don't know it, but for sometimes it's easy to, if equation is linear, then I can solve it, but equation is non-linear, then I can do iterative. But sometimes it's simply not possible, like for PDEs, partial differential equations. So one scheme is to do this, so just wait. Okay. So this is a predictor scheme, this is called predictor. Then I say that, well, my solution corrector xn plus 1 is one such scheme, okay, is xn. Now look at this. I don't know this, I think probably you use. So I am going to use this value, which is my predicted value. So what I will say is I h f half f of xn Tn, which I know, this I can compute, but f x n plus 1 star Tn plus 1. So this is called corrector scheme. So I combine this one with predictor corrector, and I will be able to solve it. I will be able to solve it explicitly. So please remember, these are the words which are quite often used, called explicit scheme, implicit scheme. So this is explicit scheme. Given xn, I can find xn plus 1 right away. This is called implicit scheme because I can't solve xn plus 1 directly, because xn plus 1 depends on xn plus 1 itself. So for complex problems, I may have to do iteratively or use something like predictor-corrector. But these schemes have a lot of value, because this scheme is stable, and we want stability. So we can do Taylor expansion, and we can show. So this part is there in my notes, so I think I'll skip it. So this one is 1 plus alpha h plus. So this is accurate up to second order. Okay, you can just do Taylor expansion and figure it out. This is accurate to second order, which is better than Euler scheme, which is only accurate up to first order. So in your project, you should do at least second order, not the first order. Okay. So another important scheme. So I will erase this. So this is called Runge-Kutta scheme. So it has second order, third order, fourth order. So I will only mention second and fourth. Also fifth order, sixth order. But I do want to make a remark here. You are supposed to take a small h, right? So let's say h is 10 power minus 4. So it's good up to 4 significant digits. Now if I use fifth order scheme, which is accurate to fifth order, so fifth order scheme will be accurate to h5, let's say. So what is the accuracy of according to this scheme? 10 power minus 20. Now should I go for these kind of schemes, or sixth order? Why not say sixth order? The problem with that will be this number will be 10 power minus 24. So my last 6-7 digits will be comparable to the random numbers, to the round off errors. I can only represent with double precision only up to 15 digits or 16 digits. Anything beyond 16 digits is not reliable. So you should not also go for very, very high accurate schemes. Okay, so that is something we should keep in mind, that we shouldn't go to like h power 6 if your h is 10 power minus 4. But indeed, if your h was so 10 power minus, with this scheme I can use 10 power minus 2 as h. Okay, so I can take a bigger time steps. Okay, so these are some engineering issues. You have to be careful when you apply your method. It's an art. I mean, you have to be careful. Okay, so how does Runge-Kutta second order work? So the idea is to go to the x mid. So I go to the middle point and find the slope at the midpoint, and use the slope to time it once. So x plus half equal to xn plus h. So it should be h by 2, right? But I am taking only half step. So h by 2 f xn t. Now I say xn plus 1 is xn, or you can call this is a midpoint, okay? Xn plus h f xn plus half So, this is my answer. It is again accurate up to, easily show this is accurate to second order, h squared. It is error of the order of h cube. So, I will not prove the stability of this. This is again more work. So, there will be a region of stability. For Euler, remember it was stable for 1 minus alpha h mod less than 1 or 1 plus alpha h for explicit. So, we can also derive what is the region of stability. So, what alpha and h combination, it is stable, but no, this is not the course. I mean, we can do a full course on ODE solvers, numerical, but I will not get into that. Now, one famous scheme is, so this is called RK2, shorthand RK2. We also have RK4, Runge-Kutta fourth. Now, I recommend RK4. Now, write down the steps. Okay, this is a bit long, but let me just write down the steps. So, it is combination of predictor-corrector. So, you can also call it predictor-corrector. Huh? So, this is like I am predicting the half value and using that I am correcting. So, xn plus 1 star half star, I just write it, huh? h by 2 xn tn. Second step, xn plus half double star. So, this is another predictor, xn plus h by 2 . So, I go to this using the slope using these values, half values. Okay. Now, then xn plus 1 3 stars is xn plus h f . So, the third one. Now, we can combine all of them, okay, the last step. So, xn plus 1 is xn using Simpson rule. So, h by 6. So, I am going to write go xn, please this is not a power, huh? So, I bracket I am kind of tired now, 2 f xn plus half star now I have two more terms, let me just write it here, 2 same thing with a double star, these values, okay. So, remember Simpson has 4 midpoint, this is a factor 4 for the midpoint. So, you combine 2 for this one and 2 for this one. Now, these guys of course are clever people, they design all these schemes, and this is accurate to h power 4, error is in h power 5. So, it is accurate to h power 4. The last step is xn plus 1. So, f xn plus 1 triple star, this one. Okay, so this is Runge-Kutta fourth order. So, you can implement it in your for your homework or project. Now, all these are for solving one equation. Now, what if I have more than one equation? Is that clear so far? I mean, you have tons of schemes. I showed how many of them? 5 of them, right, or 6. Euler forward, Euler backward. That was trapezoid, which is crank Nicolson. Then we did one predictor-corrector, that is 4, 5 and 6. Okay. So, 6 schemes, that is good enough for your course. There are some more. I may do maybe 1 or 2 when I do the PDEs. okay. But let us start with this x. So I have set of equations. So one thing could be, let us call them xi's, variables x0, x1, x2, x3 like that, xi. So xi dot will be function of all the xi's. So x0, x1, I call it up to xm minus 1. So there are xm m variables, n time. Okay. So I have these many variables. Now that is the notation. Now you can see why I changed it. So the I is for the number of variables, and this is for your time step. Now, so how do I solve this one? So I have m equations. So you write down time stepping scheme for all of them. So given vector x, so I call it a vector. So given vector x at time t, I can compute vector x at t plus delta t or t plus h. Okay, you can apply the same scheme. You can choose one of them and you can apply it. So let us do an example. So in mechanics, we have equation in 1D for a particle of mass m. Mx dot is force, which is function of position, velocity or time, or and time. I say and time. Now this is second order equation. So I should first convert it to first order. So how do I do to first order? So mx dot is momentum. So this first order. Then p dot is f x p by m t. So I have two equations, two first order equations, I can solve it. So if I were to do by Euler scheme, so I am going to take it to the left, to the right, like this. If I do Euler scheme, then this translates to x t plus delta t, x t plus h. So I will say xn plus 1, following the same notation, is xn plus h p n by m. Okay, straightforward. So given the momentum and position at time t, I can find out the value of these variables at time t plus delta t. So Pn plus 1 will be Pn plus h f. So this is how we solve it. So it could be huge numbers. If particle is moving in 3 dimensions, how many equations would I have? 6. So we have 3 second order ODEs, but 6 first order ODE. And what do they correspond to, this axis? What are they called? So why do I need 6? In fact, it is a very important physical implication. So this is the phase space. So phase space is 6 dimensional, and given initial condition which involves 3 position and 3 velocities or 3 momentum, I can find the future uniquely. So phase space trajectory you can draw. In fact, I am really solving phase space trajectories. Is that okay? Okay. So this is for set of equations which you will need it. So when I do PDEs, I am going to convert PDE into set of ODEs. So that is the idea. So convert PDEs into set of ODEs and solve ODEs by one of the methods I described. If I were to do Runge-Kutta second order, what should I do? I first go to the midpoint. No, for midpoint for both x and p. Then use the midpoint values to go to the t plus delta t. Okay, so I will not write it. But you should first think of the idea, and then you just code it. And don't code in the computer right away. You just write in a piece of paper. Okay, now the last algorithmic part is called stiff equations. Okay, so this is also important. So when I have set of ODEs, then they have different time scales, or they could have different time scales. So let us take an example. So I will just show you by an example, and we find it all the time. So the equations I am going to use is x dot plus alpha, no actually u dot, I am using u and v. U dot is this v and v dot is minus v. Okay. Now all that non-dimensionalization we did is not useless for many reasons, and one reason is to solve these equations. So what is the time scale for these two equations? What is the time scale for this? What is the time scale? What? Come on. Huh? What is the time scale? Huh? Sorry? V dot is minus v. So at what time the function will change? Come on, this is disappointing. It is 1. It is already non-dimensionalized if you think. The time scale for this problem is 1, or let us call it t. Right? This solution is e power minus t. So in t equal to 1, it has dropped by 1 by e. Okay. Please remember how to do think of these scales. What about this? So one time scale will come from here. So that is that time scale. Another time scale comes from where? Alpha. So alpha is dimension of 1 by time. So time scale here is 1 by alpha. Now here time scale is a 1, here is 1 by alpha. If alpha is too large, then these two equations are different time scales. Now you can think of two oscillators, one is very high frequency, other one is order 1 frequency. Now I want to solve it in a computer, then what should be my h or delta t? What should be my delta t? Now this is a physics aspect, I mean you guys like, so what should be my delta t? So let us say alpha is 100, okay, this is 100, and this is of course time scale is 1. So what should be my h? Less than 1 million. Okay, there is no second here. I am not. I just talk about numbers. Less than 1,000, 1 billion, 1 million, 1 by 1,000. So what should be the number? Less than 1 by 100. So you should be able to resolve the time scales. So these oscillating, you know, I mean, are not oscillating. This is decaying, but this guy is trying to push it, forcing. So you should be able to resolve the lowest time scale. So resolve the lowest time scale. If alpha is 10 or 15, then of course I am stuck. There will be too much of a problem. Okay. So then we need to come out with some more clever scheme. If 10 by 15 means my computer will just sink, it is not going to do anything. There is too tiny a time scale, 10 by minus 15 will be too tiny. Okay. So these are the situations which occur in nature, like oscillations at all these big fast lasers, they have very high frequency. Okay, femtosecond laser or what is the petawatt lasers, so they can correspond to this kind of situation. Okay. So how do we handle this kind of problems? So these are called stiff equations if the two time scales are far apart. Okay. So you need to worry about stability and accuracy of the systems. So one way is to, so one thing is that I hope you understand that you need to resolve both the time scale for accurate simulation, but there are ways to overcome this. So one clever way I will tell you is that I can make a change of variable for this equation. So, if I make a change of variable, so u tilde is u e to power alpha t. So, u tilde is a new variable. Let us take a derivative, u dot is u dot alpha t plus alpha. So, now I got u dot plus alpha u. Okay. So, I can now use this idea. So, the left hand side can be written as this, right, u dot plus alpha u is that clear, equal to v. So, my u dot is v alpha t. So, I got rid of my problem case alpha u term. Okay. Now, I have, this is order 1, no problem. So, you can solve this v dot is minus. Okay. So, this is exponential, this is called exponential trick, and this has solved my problem. Okay. So, this is one standard trick to be able to use higher delta H. Other thing is to use Crank-Nicolson scheme, the one which I just said. Crank-Nicolson scheme lets you use bigger H because it is stable for bigger H. It will not be accurate, but you do not need to take very tiny time steps. Okay. Now, so if I use Crank-Nicolson scheme, what will be the time stepping for this? So, I use Crank-Nicolson. So, it is going to be u dot is minus alpha u plus v. So, un plus 1 is un minus, so plus h by 2 at n and n plus 1. So, minus alpha n plus vn minus alpha now rearrange it. So, take n plus 1 to the left, I get un plus 1 is un plus, well, this is going to be absorbed here, 1 minus alpha h by 2 divided by 1 plus alpha h by 2. So, this is un part and vn part you have to also divide. Okay. Now, this is the stability, this will give you stability. Okay. So, Crank-Nicolson is a nice scheme for solving systems where alpha is so give stability of two stiff equations. Okay, that's, so you kind of remember this one, and we will do it when we do PDs. Okay. Okay, so I finished ODE solvers. So let me just do some demos. So is that clear or is it like not clear? Okay. So this part requires proof, but you can see this is a nice trick and you can use it also. Okay. So this is there are 3 solvers for Euler explicit, Euler implicit, okay. So it's straightforward. I mean, this writing is easy, right? I mean, so Euler explicit is clear. So, given f, any function f, I have to give initial condition and final condition dt, sorry, t init, t final and dt. So, this is initial time, final time, dt and initial condition. So, give me this, I will tell you the time and x, the full time series. Okay. So, so the loop, so this is going to be in a loop. So, I just say how many n I require, t and x, x0 is assigned with initial condition and I do a loop. So, xk is fxk tk times dt, dt is h. Okay. So, this is already explicit, everybody agrees with that. So, I can get return tx and that is the answer. So, let us do an example. So, this is my f. So, I put my f here, t init is 0, t final is 10 and dt is 0.1. Initial condition, I say my value of the function is x, 1 unit. So, my equation remember is x dot equal to x, x dot equal to x. So, my solution is x0 e to the power t, it is growing, my dt is 0.1. Okay, you have to come closer. Huh? So, let me run this one. Actually, this doesn't come very nicely. Let me just open a new window. Okay, run Odie. So, my answer is in t comma x. My answer is here t comma x. So, I can plot t comma x, plot t comma x. So, this is a plot. Now, how good it is? It is exponential, it is growing indeed. So, how good is it? So, I can put the to the exact value, this is straightforward, no, exact values. So, let us put that t comma, so I will put this in red, t comma is exponential exp t comma rg green. Okay. Now, this is the correct value and this is my value coming from the numerical code. Now, you can see the error is huge. So, these are around close to 15,000, 14,000 and the exact value is close to 22,000 at t equal to 10. Okay. My h was of course too tiny, not too tiny, 0.1, too big, and this is a first order scheme and error will keep growing. So, it's a, we can see it's a bad scheme. Let us do the implicit scheme. So, you play around with this, huh? So there are various options, you change h. So this implicit scheme is here. Now, so I said xk divided by 1 minus, so 1 minus alpha, 1 divided by 1 minus alpha h. So this is derived in the class. This of course works when I can take it to the left hand side. For linear equation, I could take this to the left hand side. So this is, now you have to take your, look at your notes. So this is what I have done in my notes. Xk divided by 1 minus alpha h. So this is alpha h. So this is stable, and you can also do, yeah. Okay, so let's do this one, implicit. Now I want to, so this for complex z. My initial condition is 1, and so remember I had, this is for, where is my, so this one g. So z dot is I pi z. Okay, let's put a minus because in the class I had put a minus sign. alright. So, let us run it and my answer is in Z2, my answer is Euler implicit Z2. Okay.
So,
yeah.
Euler explicit previous one also.
The outcome
If here e comma x is for
this f you mean?
yeah. So that f is the return value of the function or the function?
The function itself. So, the function, this function I call from here and this function is defined here. So, you send the function itself. How it does inside is not our problem, you just send the function. Okay. So, I am going to look at Z2 and Z2 is complex, so it has real part and imaginary part. And so, solution is straightforward, no, is Z0 e to the power minus I pi t and Z0 is 1 is oscillating. So, let us run again. Now, I have to real of Z, it was t, no, t real of Z2 and what is real of this one? Cosine pi t, cosine pi t. Cos should work. Where is the figure? Okay, so let us kill this one first. Okay, so which is my correct value and which is my numerical value? Correct value is this oscillation, right? Cos t. My numerical value is going to 0. It is not unstable, in fact, it's stable, but it's going to 0. So, these are the issues. You may have computer, we have very good computer, but we don't have good scheme, it's not going to solve your problem. Okay. So, I had to use my h small, that you work it out, okay. I mean, my time is running out very soon. So, you have to use small h and higher order scheme. So, Runge-Kutta 4th order is going to do better. Now, Runge-Kutta 4th order, please implement it. Yeah.
Definition of f or g. They have given the parameters as x and t, but when you are using the t inside the function.
That's right, it does not matter. So, it is going to, if it is t is not there, it will just put x.
Even if it takes
Yeah, so whatever x is there, it will put the first argument, second argument. The computer only understand what is the first argument, second argument. Okay. So, let us solve one mechanics problem. So, I will close this one. So, I will leave these codes in the drop box. So, we want to solve oscillator problem. Okay. So, oscillator problem is here. So, x double dot is minus x, oscillator with frequency 1. So, I converted to two first order equations. So, I have written here dot of y0 is 1. So, this is like position and this is momentum, and dot of p is force. So, I can do Euler. So, this is what is coming here. So, the first is, this is a time stepping up momentum, there is a force here and this time stepping up position. Now, it is going to give you y0, y1. Okay. So, this is something you have to keep in your mind, y0 is position and y1 is momentum. It gives an array of, so you have to create an array, the first one is first argument, second argument. So, for my mechanics problem, I say the first one is velocity, position, and second is velocity. So, this is going to do that work, and I can solve it. So, T Euler and T y Euler. So, I push in here f with initial condition, final condition dt. So, let us see quickly how it works. Oh, sorry, I made one mistake. So, if I had 2 of them, then I had to give you both. So, x dot is momentum. So, now this is x dot is momentum and p dot is minus x. So, this is x y 0 and this is y 1. So, what is y dot of 0? Y 1. And what is y dot of y 1 dot? Minus y 0. So, this has to be provided using Odie int. Okay, I am mixing up, I am slightly mixing up. I also do not remember all the code. So, for my code I need only f. This is what is coded by me. Okay, so my code I just need f, and if you run it, you will get T Euler and Y Euler, and all my results are in Y Euler. Okay, so you can run it, and you will find it will be oscillating with errors. Now, Python also gives its own Odie solver. Okay, so Python Odie solver is called Odie int. This one, Odie int. Now, what does Python Odie int want? It wants what is y dot. So, it can also solve set of ODEs. So, you have to give derivative for each variable. So, this is what I was writing, y dots, and that for Odie int I need this y dots. Okay. So, Odie int is a very useful function, you do not need to code yourself, and this is reasonably accurate. In fact, you can also specify accuracy. So, y init and t. Y init will be, it has 2 arguments. Y init is, first is position and second is velocity. So, initial position is 1, initial velocity is 0. So, this is, I supply all this here and I will get the result in y, result will be y, and of course t you have to create beforehand. So, this is time, lean space. So, you give it t y initial and your y dots, you do not need to give dt, dt it will compute itself. Okay. So, t array, so it will not tell you what function is using, which scheme is it using, but you specify the errors if you want, and they will give you reasonably accurate answer. Okay. But so this is what you can use it for your project, no problem, but you should also, if I tell you that you use Euler scheme, you should use Euler scheme. Okay. It is also a good idea to know what those schemes do, because in large project you are not going to use Python Odie int. This is only for a course, tiny 5-minute project. If I am running on a supercomputer, I can't use any of this. So, that time I have to be careful which scheme I should use. Okay, so I will stop.